Okay, so last time we were talking about partial derivatives, and I showed you algebraically how we describe the partial derivatives, how you compute them, how that sort of goes down in terms of shortcut rules and that kind of thing. But now the next natural question to ask is, does this mean anything, or is this just a made-up game involving symbolic manipulation that we can't actually connect to anything useful? Right? Is it always an important question when you define some object algebraically? You better make sure that it makes some sort of geometric sense or physical sense or something like that. Otherwise, you're just playing games. So is there a good geometric interpretation? Well, very importantly, and I already kind of talked about this, but it really depends very dramatically on what kind of a picture are you looking at. So reminder, we talked about when we were looking at level sets and graphs and all that kind of stuff, right? That the interpretation of calculus is going to look really different. We're going to have a different calculus of graphs and a different calculus of level sets, etc. So here we are. So I'm going to start by talking about what you might call the calculus of graphs, or part of the calculus of graphs as it pertains to partial derivatives anyway. So every picture that we're going to draw in this discussion is going to be a graph while we're looking at this question. Okay, so here's a function. Specifically, notice we're looking at the graph, right? Because we're setting the output value equal to z. So we're looking at the graph of this function, and we're going to look at the following point, a comma b. So here in the domain, if you will, in the xy plane, and we want to then talk about the partial derivative with respect to y of this function f at that point. All right. So what would that look like on this picture? Well, the good news is that this construction that we have for taking a partial derivative, you can take a partial derivative with respect to y. Each of the two steps involved in computing that partial derivative has an existing geometric interpretation, and all we have to do is really kind of connect the puzzle pieces together, and the answer is going to kind of fall into our laps. So here we go. Remember, step one in computing the y partial is to fix all of the other variables, and of course we're taking a partial with respect to y. There is only one other variable, that's x. So we're going to fix x. Now keep in mind, we are looking at what happens at the point a comma b, right? So when we say we're going to fix x, we're going to fix x at the value that it's at, right? So we are looking at a point where x is a. So we're going to fix x equal to a, and that gives us a plane that looks about like that, corresponding to where x is equal to that value a. All right, how are we doing? Is everybody on board? Okay. All right, so boom, there's our first part of our geometric interpretation. This algebraic process of fixing these variables geometrically, it's looking at the graph context. That just means we're going to take a vertical cross-section perpendicular to the x-axis, because that represents a constant value of the x variable. All right, is everybody okay? Okay, now when we do that, of course, when we take this cross-section, notice that gives us a curve. Specifically, I should say, the original graph that we were looking at was a surface, and this x cross-section, by x cross-section I mean fixing a value of x perpendicular to the x-axis, will give us a curve. And in fact, if you think it through, what are these values? What are we looking at here? What are these heights? What is z there? Well, it's f of x comma y, but don't forget x is fixed. X is now not allowed to change. X is a constant. So really we have z as a function of a single variable y. And furthermore, this curve itself, height, right, is representing the value of the function, and the single variable y represents this direction, namely the direction parallel to the y-axis. So, in fact, this curve is not just a cross-section of the original surface. This curve is the graph of this new single variable function where z is a function of only y, with the understanding that x is fixed. All right. So, next step. Next step is take the derivative with respect to your single variable. And when I say take the derivative, I mean the single variable derivative. So taking the single variable derivative, when we're already looking at a graph, we're looking at a graph of our single variable function. What happens when you take the derivative of a single variable function? Specifically, what happens in the context of the graph when you take the derivative? You get the slope. It's our old interpretation, our existing interpretation of, whoops, I missed. There we go. Our existing interpretation of single variable derivatives. So there you are. That's the interpretation of the partial derivative with respect to y. It's the slope of this tangent line to that curve. That curve being the cross-section perpendicular to the x-axis of my original graph. And let me say that a little bit differently. Notice cross-section perpendicular to the x-axis is also a cross-section, you might say, in the y direction. Right? So, I mean, that's just, if you're fixing a constant value of x, then that plane kind of points in the y direction. So, all together then, here's our nice little summary. If you want to take a y partial, and if you want to understand that geometrically in the context of graphs, the y partial is just the slope of the tangent line. Of course it is. That's, derivatives, graphs, slope of the tangent line. That's old news. Slope of the tangent line to the graph in the y direction. There we are. Nice little pithy-ish description, geometric description of how to interpret partial derivatives. Okay. Now, I'm going to leave an exercise, and I think this is a healthy exercise. I think everybody should do this. This is a good little bit of, mathematical challenge to test how well you understand this and to identify any holes that you might have in understanding, this argument that we got to here is try to copy that argument, adapt it appropriately, of course, to arguing this result that I'm just going to claim, right? And that is that the x partial is the slope of the tangent line to the graph in the x direction. Right now it's going to be a different picture, and different variables are going to be set equal to a constant, and they're going to be set equal to a different value, and everything's going to be a little bit different. But it's very analogous. Right? So what I would encourage you to do is study this argument to your heart's content, right? Make sure you're really comfortable with this y partial argument, and then put it away, take out a blank sheet of paper, and see if you can produce pictures and the algebraic details, produce the argument that comes to this conclusion. And if you can comfortably, and if it all checks out and looks good and works out, then you're good. And if not, then you've got something to ask questions. And I'll remind you, my office hours, the other two instructors' office hours, you're also very welcome and invited. And then also the help room, which is a great resource. Open, 2 nights a week, 7 to 10, if I remember correctly. Okay. All right. Okay, moving along. Now, reminder, again, the geometric interpretation of partial derivatives depends on what kind of a picture you're looking at. So the calculus of graphs is one thing we just started talking about a little bit, right? We've seen some of the calculus of graphs, namely what do partial derivatives look like on graphs. Okay, what if we're not looking at a graph? What if we're looking at this, again, what I call the literal picture that we talked about? In what way would we see the partial derivative on this picture, or at least what does the partial derivative relate to that I can see on this picture? What's going on? How would I visualize, how would I describe partial derivative in this context? So, now you'll notice here I'm taking a higher dimensional function, taking a function of 3 input variables. just to emphasize that we kind of have to use this literal picture here. The graph is not an option here. You can't do it. That would require 4 dimensions. It's not we can't do it. Okay, so if we are at this point, and at that point I want to compute the partial derivative with respect to y. How does that work? What's the deal? Well, keep in mind, again, first step, we're taking the y partial. So we're going to be moving in the y direction, and that means that x and z are to be held constant. That means we're going to stay entirely on that line where z is whatever constant value it is, c, and x is whatever constant value it is, namely a. Right, so those are fixed. Z and x are fixed, and that means we're moving along this line in the y direction. Okay. Everybody with me so far? And I can talk about, by the way, what would happen if I were to change my input as I move in that y direction by some amount, dy. Right? And we can talk about the differential output as I move in that direction by some amount. Well, then the output, we would estimate its change by some amount, differential amount df. So we have an input change, we have an output change, and one of the interpretations we have from single variable calculus is that a derivative is a relationship between input changes and output changes. Right? In this case, and this again is just a recall from single variable calculus, the single variable derivative is the thing that you multiply times your input differential to get your output differential. Right? That's just a recall from single variable calculus. So can I point to the partial derivative in this picture? Not really. It's not exactly over here or over here, but it's a relationship. It's this multiplicative. It's this factor that I multiply by that to get this. So it's a relationship between things that I can see. How we doing? Everybody happy? Okay. All right, what if we're looking at level sets? Right, now again, it's going to be different, right? I mean, the calculus of graphs, the calculus of the literal picture, I guess you might call what we just talked about. Now we're going to talk about the calculus of level sets. Same partial derivatives, exactly the same construction, but on a different kind of a picture, so it's going to look different. And don't, for example, make the mistake of thinking that, I see a curve, and so, somebody said something about a derivative, so I guess derivative must be the slope of the curve. Not at all. Right? This would be dramatically wrong. This would be trying to interpret, in a level set context, trying to interpret a partial derivative in terms of the calculus of graphs. This is not a graph. So it's complete disconnect, doesn't make any sense. Is everybody with me? We're going to have to figure out now what is the calculus of level sets, how do partial derivatives kind of, in whatever sense we can, how do they make geometric sense in this picture. So my own personal favorite intuition is to think in terms of, contour maps, topographical maps with the contour lines. I'm going to try to trace there we go, okay. So there are some contour lines. And just imagine you were hiking, and how would you feel if you were asked to hike in the x direction, right? Per this partial with respect to x, this says move in the x direction. Well, that looks like a pretty tough hike to me. Right, you're going almost exactly straight up the mountainside. Straight uphill. No, you don't get the benefit of any switchbacks or any clever thing like that. So you're going straight up the side of the mountain. That looks hard. That means the graph is steep, and so the x partial we would expect to be large. Everybody on board? Seem like a reasonable thing? Now let's think about what if we went in the y direction. Well, if I could draw a straight line here. If you're going in the y direction, well, in the y direction, you are still eventually getting from this contour line up to the top contour line, but notice it takes a lot more distance. Right? You've got to go a lot farther. You've got to go, this far to get up those two contour lines as opposed to merely that far. Right? So you're gaining the same amount of altitude over a much longer distance. This looks like a much more pleasant hike. I think that the slope of the graph, namely the steepness of the mountainside, should be relatively small. Does that make sense? Now, the bad news is that in this picture, the way I have it drawn and, with no annotations, I can't tell how large or how small, right? I don't know how many feet difference are there between each of these contour lines. How much horizontal distance is this, right? I don't have a legend to work with, and I got no labels on my contour lines. I can't actually find the values, but you can sort of see relative relationships of, which one's bigger, which one's smaller. What do you think? Everybody all right? Okay, moving along. So next thing we're going to talk about is sort of a kind of an application, you might say. We're going to develop, we're not going to answer a real world problem with math. We're going to develop more math with that math. We're going to use partial derivatives to develop something called a linear approximation. So first, just a little bit of terminology. The linear approximation, by the way, here's the formula for the single variable linear approximation. I hope you all remember this, right? Single variable linear approximations. And amusingly, they're not linear. Right? To be a linear transformation, you can't have a constant term. The L of 0 would have to equal to 0 if it were actually a linear transformation. So it's not linear. The word is affine, but y'all don't need to worry about that. There is something related to linear approximations that actually is linear. So the name is not entirely ridiculous. It's just that we're going to have to kind of pause and wait for that to reveal itself very soon. Okay, next little disclaimer I have to throw out. The initial conversation I want to have with you all about linear approximations, I want to assume that the linear approximations exist. I want to assume that there actually is such a thing. In some situations there really isn't. Depending on how ugly your function is, what kind of bad news is involved with your function, there might in fact be no linear approximation. If there is no linear approximation, don't try to write down a formula for it, because it doesn't exist, right? So I don't want to have to deal with that for the moment. So for the moment, I'm going to say let's assume that it exists, and then we're going to come back in a couple of pages and worry about, okay, well, if it doesn't exist, what would that mean, and how would I detect that? Okay. So assuming now that it exists. So I'm going to, again, work off by analogy from the single variable case. So single variable, old formula for the linear approximation. And lots of different ways that you could think of how to motivate this or describe this. Here's one that I think works really well here. I claim that this function right here, this polynomial, is the unique degree 1 polynomial that has the same value as f at the point A, and it also has the same first derivative as f at the point A. And there is only one polynomial that can possibly have this feature, the degree 1 polynomial that has these two characteristics. So same value as f, same derivative as f. You might say this function, this linear approximation in green here, is, in terms of value and derivative, it is just mimicking the function. It's just doing its best to impersonate the original function f. Y'all okay with that? That sound familiar? Okay. All right. So, I'm going to use that to motivate this formula here for the linear approximation of a multivariable function. Now notice this is a multivariable function, but it is still real valued. And we'll talk in a few minutes about what to do if it's not real valued. What if it's vector valued? Right? How does that change things? But let's put a pin in that. For the moment, real valued only. Okay, so for such a function, I claim that this thing right here is the unique first degree polynomial that agrees with the original function f in value and in all of the partial derivatives. Right, so this is the application that we're making of partial derivatives. We're going to use partial derivatives as a tool for defining what we mean by a linear approximation. Now, I owe y'all an explanation of how is it that this function, in fact, agrees with f in terms of value, and it agrees with f in terms of all of its partial derivatives at the point A. So, here we go. How do we know this is true? Well, at the point A, at the point A, if you plug in x equals A into this formula, then that's 0 and that's 0, so all of these terms go away, and sure enough, you just get L of A is f of A as desired. So that the plugging in part, that's pretty straightforward. Now, to talk about these partials, I claim that the partial of L with respect to x1 is equal to the partial of f with respect to x1. This is all, of course, at the point A. Now, how do I know that's true? Well, we're going to have to be a little bit more careful. Let me remind you, when we're taking a partial derivative, we've got to keep track of what's a constant and what's not a constant. So I want to, before we get into the actual taking of a derivative, I want to look into this function and write down what's a constant. So for one thing, f of A is a constant. It doesn't depend on x at all. It's just some value, whatever it is. Take A, plug it into f, you get a number, that's it. It doesn't depend on x. Likewise, this partial derivative, constant, this is not the function that you get when you take the partial of f with respect to x1. This is the value that you get for that partial derivative when you plug in the point A. Notice that, by the way, this vertical line right here is just an alternative notation for saying I'm going to evaluate this function at whatever this point is down at the bottom of the line. So this just says at the point A, what's the value of that partial derivative. So again, that's just a number. And x can change, but that value doesn't. That's just some value. Ditto all of these other partial derivatives, all constants. And then, of course, the point A isn't moving, right? That's all constant. So all of these coordinates, A1 through A, those are all constants. So we got a lot of constants in here. And now, keeping in mind that I'm taking the partial with respect to x1, this x1 is not a constant. That's a variable, but it's a partial derivative, which means all of the other x's are constants for the purpose of computing this partial derivative. So again, while I'm taking this partial with respect to x1, like this xn right here, constant, right? Which means you'll notice that this entire term is all constants, and so are all of the other terms other than the x1 term. All constants. Just everything in the entire term, all constants. So when you take the derivative, all that just goes away. Right, and likewise f of A, that's just a constant, so that goes away. So when we're taking the derivative here with respect to x1, all we're really taking the derivative of is a constant times x1. That's it. And that derivative is, of course, just whatever the constant is. And so, as desired. Is everybody with me? Everybody's happy? Okay. All right. So now I've just done the argument for the x1 partial. I want to encourage y'all to take a stab at showing all of the others. It's going to be highly analogous, pretty much the same thing, right? So as necessary, listen to this recording again. Keep in mind YouTube channel and all that. Listen to this explanation again of how I confirmed this for the x1 partial. Make sure you understand that. And then once you feel like you have a good understanding of that, take out a clean sheet of paper and try to reproduce the argument for these other variables. Okay, good practice problem. Okay, now let's take a careful look at this part of the formula. That's just part of the formula, of course, but there is something very special to observe, and that is, it looks like a dot product, just structurally. It's a bunch of terms, and each term is a product of two factors. So I feel like what we've got here is a bunch of factors that look like that, and then we've got a bunch of factors that look like this. And that this, in purple then we have basically a dot product of a green vector with a blue vector. Yeah.
What is the line to the right of the derivative?
Yeah, so that's just a notation that means evaluated at a given point. So right here I've got partial of f with respect to xn. That's a function. But when I say vertical line, that says, but evaluate this function at then this point, whatever point's down there. So it's equivalent to putting it in parentheses. And the only reason I don't use the parentheses is because I always think it looks weird to have a function and then parentheses and another parentheses, and I feel like it looks like you're multiplying instead of evaluating. I find it confusing. This is, to me, reads on the page a little bit more comfortably. But it's just a notation. Yeah. Okay, so we've got this as a dot product. Now, furthermore, not only is this a dot product, the blue one is one that we already recognize. What we have in blue up here are literally the coordinates of the vector x minus a. That's a natural thing, right? We're doing a linear approximation at the point A. We're at a nearby, hopefully, presumably, a nearby point x, and that difference vector is exactly what has coordinates that we have in blue up here. So this is starting to look pretty useful. This bunch of stuff that we have in purple, not only is it a dot product structurally, it's a dot product with something natural. And that makes us highly suspicious that whatever this thing is in green might also be actually a pretty natural thing. So we're going to give this a notation and a name. The notation is this funny looking upside down triangle. And the name is, we call this the gradient of that function. I'm using G here instead of F. This is just intended to be a generic statement. So that's all. Okay, so with that in mind then, all of this stuff is the gradient, and then I have to zoom out one more notch. Sorry, I know that's small. But then all of that stuff up there in purple, all these bunches and bunches of terms, that's a single dot product now. What do you think? It's just notation. Right? It's just kind of a notational alternative. But it is nice if you have a bunch of terms, being able to see meaning inside of just a bunch of terms is very valuable. And we already know 2 bits of meaning here. X minus a means something. That's meaning that we understand. So we're relating a bunch of gobbledygook down to something that means something that we know. And the second thing that we know, dot products. We know about dot products. They're geometrically natural. There's the potential that having written this as a dot product and understanding dot products as we do, that could help us understand what this means also. Okay, so this is a very substantial improvement. Alrighty.
So the gradient's a vector?
Yes, that's right. The gradient of a real valued multivariable function is a vector. And interestingly, notice it's the vector made up of just all the partial derivatives. Oh, absolutely. Okay, so let's do one. Here we go. we want to find the linear approximation of this function at that point. So, well, again, we have a formula. Here's our formula for our linear approximation. And so you'll notice that's all I've got here. I'm just writing down the formula. All we're doing is plugging in. So, for example, I've got to figure out what is f of a in this scenario. Well, I got to take this point A and plug it into that function f and do the arithmetic, and out comes 5. That's just arithmetic. Okay. Okay, let's see here. Oh, real quick while we're here, x minus a, well, x, I missed again, x has coordinates x comma y, and a has coordinates 1 comma 2. So x minus a is easy to write down. Yeah, everybody see what happened there? And then all that remains is we've got to figure out what this means, gradient of f at a. Well, per the formula that we have up here, gradient is computed by a bunch of partial derivatives. There's 2 input variables here, so we take the 2 partial derivatives. We do have to evaluate it at the point 1, 2. And so evaluating at the point 1, 2 all together, when you plug in that point 1, 2 into each of these formulas, then the gradient vector turns into 2 comma 4. And so our gradient vector right there, 2 comma 4. Everybody follow. Feel free to ask a question. Okay, so now having done the plug-in chug, yes, we could, I suppose, take all this and kind of dot it out and multiply, collect terms, etc. You could rewrite it as this. In practice, most of the time, I don't really see the point of that. I mean, I suppose if you're programming this into a computer and you want it to be as lean and tight as possible, then yeah, this is a little bit more computationally convenient, I suppose. But unless you're doing that, it's actually most of the time more helpful to be able to see the structure of the formula. So I would just leave it like this. Certainly on any of my exams, unless there's some aspect of the question that would suggest otherwise. If the question just says, find the linear approximation of a function at a point, just leave it in this form. You don't need to multiply it out. That doesn't bias anything. All right. Okay, so what happened again? I wrote down a formula. I confirmed that it has key properties that justify calling it the linear approximation, and then we came up with a notational convenience to redefine what to do with all these partial derivatives, and namely the gradient was our notational convenience there. All right, now for the next question I'm going to ask, I'm just going to let's keep away from the ugly notation. I'm going to start with the notational convenience. Just to save us some otherwise really nasty formulas. So here it is. I'm going to define this matrix called DF. It's a matrix. This, by the way, this is in respect to considering a question of a multivariable, vector-valued now function, right? So vector-valued instead of real-valued. And what we're going to do, this matrix, the way we're going to arrange it, notice it's made up of just a bunch of partial derivatives. And again, y'all know how to compute partial derivatives. But we have to arrange those partial derivatives in a very particular, non-negotiable way. And this is, by the way, not a convention. This has to be in this particular arrangement. So here it is. Notice that in this first column, all of the partials are with respect to x1. So I'm going to call this the x1 column. Because every entry in that column, the common feature of the entries in that column is they are all partials with respect to x1. Okay, and then likewise, of course, in the same way that this is the x1 column, Next one's x2 column. Next one's the x3 column. The last one is the xn column. Everybody happy? Let's see here. Now let's talk about the rows. The rows mean something too. If you look at this first row, notice the common feature. Every element in this row, we are taking a partial of F1. We're not always taking the partial with respect to the same input variable. We're always taking the partials of the same output variable. So this first row, I'm going to call the F1 row for that reason. And then likewise all the way down and all the way down to the last row, we're always taking partials of FM. So we'll call that the FM row. Is that
yeah.
Yes.
Is this the Jacobian matrix?
It is. It is. We'll get around to giving it that name very soon. But yes, absolutely. Okay, so this is a notational convenience. Again, what did we do with our gradient notational convenience? Well, it made it easier for us to write down. This was kind of a long and uncomfortable thing to write down. Much more compact to write it down like this, right? Definitely nicer. And so I'm just going to start with the convenient notation then for this situation. And here it is. If you want to do a linear approximation for a vector-valued multivariable function, there's the formula. And I assert, and y'all can check me on this, and in fact you should, I encourage you to check me on this. This function agrees with f in value and in all of the partial derivatives, by which I mean all of the partials of all of the output variables with respect to all of the input variables. Right? So there's an entire array, an entire matrix, in fact, of partial derivatives of the various outputs with respect to the various inputs, and they all agree with f. Thus, again, reasonable to call this a linear approximation. Okay, now, in order to actually confirm this, golly, there's a lot of dots going on in here. So maybe don't bother, just to avoid notational awkwardness, don't bother doing this in general. But I think it'd be a really healthy exercise. Take a 3x3, right, where you have 3 inputs and 3 outputs. Your matrix here would then be a 3x3 matrix. And with the understanding that that's the matrix here in this formula, then write down the various partials of this formula and confirm that you get, as required here, the various corresponding partials of the original function f. It's going to be very analogous to the argument on the previous page. Okay. All right. Pausing. Example to follow in just a second. Everybody's good. Okay, so here's a multivariable function. 2 inputs, 3 outputs. Now note, because we have 2 inputs, we therefore have 2 columns. In fact, let me color code to be better about this. 1 input x gives us the first column of our matrix. Second input y gives us our second column of our matrix. So in particular then, this first column is all the x partials of the various components of f. Second column is all of the y partials of the various components of f. Okay. And then further notice, because we have 3 outputs, we're going to have 3 rows. For the first output, we're taking the partials of the first that give us the first row. For the second output, the partials go in the second row, and for the third output, the partials go in the third row. Okay. All right. So with that said, various partial derivatives. Make sure you can do that. Right? Partial derivatives, again, they're pretty easy to compute. You got to keep track of what variables are playing what roles while you're taking them. And it can be extremely confusing because if you just got through taking an entire column's worth of partials with respect to x, where you were treating x as a variable, then when you get over here to start taking these, you got to remember, okay, x is no longer a variable for the purposes of these partials. Now x is a constant. And, got to keep track of that, so it can be confusing. You plug in, you plug in the point, and this DF matrix turns into that. And then here's our general formula for linear approximation, and plugging in the details. The DF matrix we just computed above. X minus A, of course, as usual, easy to write down. And let's see, the value of the function. Okay, this is annoying, but you do have to plug in plug in A into F and get the actual value of the function as your starting point. Everybody good? All right, so those are linear approximations. We are going to move on. A couple more things I should say. Sorry. These are quick. I've already kind of said most of these, but we've already talked about how all of the entire first column are all partials with respect to x1. Another way to say that is to don't forget that f is a vector-valued function, and when you take a partial derivative of a vector-valued thing, you're going to get a vector of partial derivatives, and that's what this first column is. So this is a kind of a notational, this is a way of thinking about it. And then likewise, the rows are all partials of, let's say first row here is all partials of F1. And in fact, if you think about it, the collection of all of the partials of a given function, in this case F1, is the gradient. That's exactly what we wrote down a couple pages back here. The gradient is a vector consisting of, all of the various partials of that function. So, handy relationship then between this matrix that we're working with and the gradients. Okay, last observation. We've already agreed L is not actually linear. It's kind of awkward, right? They call it a linear approximation, but it's not linear. That's annoying. The reason they call it a linear approximation is because the thing that's doing most of the heavy lifting there, being as it is a matrix, is linear. So, there's a constant term in there, okay, whatever. But the thing that's doing the work is a linear thing. Okay. All right. So, let me remind you, back to single variable calculus. If you are doing a linear approximation, and here's our formula for the linear approximation for single variable. The linear approximation is a new function. A lot of people accidentally conflate the linear approximation with the tangent line. And again, you can kind of get away with that in single variable, but it's a problem in multivariable. We're going to, in some cases, be talking about a tangent line with no reference to the linear approximation and vice versa. So, what is then the relationship between the tangent line and the linear approximation? They're not the same thing, but they are closely related. The tangent line, after all, is a geometric thing. The linear approximation is an algebraic thing. This is a formula, right? It's a function. And this is not the picture. Right? So the relationship, of course y'all can read right off of the thing here. The relationship is that the tangent line is the graph of the linear approximation. The tangent line is what you get when you take your linear approximation and set it equal to a new variable, usually y, and thus giving you an equation, and you can draw it, and it's the tangent line. Okay. So, not the same thing. Connected by way of the graph construction. Okay, so again, that's just kind of cleaning up a common sort of sloppiness in single variable. So, having noted that, it's the exact same deal with functions of multiple variables. you can talk about the linear approximation. We're looking just at real valued functions here. It's just harder to draw the picture for a vector value. But here's our general real valued linear approximation formula. And if we take the graph of that linear approximation, that then gives us an equation, involving 3 different variables, 2 inputs, 1 output, and that equation involving 3 variables gives us the tangent plane to the graph of the original function. Okay. All right. Cool. So moving on now to sort of cleaning up some of the stuff that I swept under the rug several pages back. You may recall that let me just actually go to it. When we first started saying, hey, let's consider linear approximations, I said, hey, golly, there's a bunch of bad things that can go wrong here. Why don't we assume that there's no problems, that nothing bad happens, that the linear approximation actually exists and everything's fine, and then if it does exist, what would it sort of have to be, and all these formulas follow. But now I'm going to ask the question, how do we know if it exists? What should it even mean to say that the linear approximation is in fact a real linear approximation? And how do I know, other than extensive ugly work, how do I know if a linear approximation actually is what we claim it is? So I'm going to start with a problem. This is one of the kinds of things that we ought to be worried about. There's a perfectly reasonable function. Now, I'll confess this is a weird function, but it's nevertheless a perfectly well-defined function. It's defined to have value 0 most places. So I'm drawing in this picture here, by the way, I'm drawing the graph, and you can see all these points in yellow where neither x nor y is 0. All these points in yellow, the value of the function is just 0. So the function is 0 in most places, but if either x or y is 0, in other words, if x is 0, namely on the y-axis, or if y is 0, namely on the x-axis, for all of those points, the value of the function is 1, not 0. And so above all of these green points, the value of the function is 1. So I'm going to push up on the picture, as we imagine these things. Push up by a distance of 1. And so the graph above these green points, the graph is, it's kind of that elevated line and this elevated line. Does everybody see what I'm talking about there? It's a weird function, admittedly weird. But perfectly valid. As a function, no problem. Okay. So that function being defined as it is, let's entertain the question of what is, at the origin. Looking at the origin, where of course the value of the function is 1. What's the linear approximation at that point? Well, in order to form a linear approximation, I need to know the value of the function. Good, I already have that. It's 1, no problem. And I'm also going to need to know the gradient. Now the gradient, don't forget the gradient is made up of partial derivatives. So this first entry here, that's the partial derivative. As I move in the x direction, how does the value of the function change? And notice, it doesn't change at all. The value of the function is 1 when I'm at the origin. And as I move exactly in the x direction, I'm moving right along the x-axis where the value of the function remains 1. And the derivative, therefore, as I move in that direction, is just 0. And then likewise, as I move in the y direction, I'm staying on the y-axis where the value of the function remains 1. And so that partial derivative also 0. So there's no problem at all in writing down what the linear approximation of this function is. The linear approximation of the function is just 1 when you're at the origin. Correction, our formula, our existing formula for linear approximations is just 1. So let me draw a picture now of this linear approximation, this candidate, this would-be linear approximation is just this plane up here where z equals 1. Is that a good approximation of the function, which you see down here is 0, and it's 0 for like all, as you approach toward the origin, you're getting really, really close to the origin. No matter how close you get to the origin from this direction, the value of the function stays 0, and yet we're claiming that all these zeros are well approximated by this constant function 1. And no, that's just it would be unreasonable to call this truly a linear approximation of these values. So what we have here is that even though all the partial derivatives exist, even though you can write down the formula for the linear approximation, it's a stinker. This is not a good linear approximation. So we're going to have to figure out what went wrong here, and how do we clean that up, and how do we come up with a good criterion for when this works. See y'all later. Have a good rest of your Wednesday. As usual, stick around and make sure I mark you down on attendance if you came in after I did that.